vector and the electric wave. So these two things are two different things. They're separated from one another based on the understanding around the turn of last century. Okay. Now, in 1905, though, Albert Einstein published a paper on photoelectric effect, which led to the quantum revolution. What we have observed in the laboratory is that EM radiation sometimes behave like small particles. Well, that's contradictory to then current understanding. Electromagnetic radiation are waves, they're not particles. But they do actually behave like particles, the electromagnetic radiation. So that's something that needs to be addressed in using a new theory. Now, what the photoelectric effect does is that an experiment easily done today in the laboratory there, if you have a piece of metal, you hook up that piece of metal to an ammeter where you can measure the current flow. And when you shine lights on that surface of that piece of metal, sometimes you detect electricity, electric current. Sometimes you don't. Okay. And the photoelectric effect there is that certain metals will release or eject electrons when light strikes the surface of the metal. So we say, well, light is a radiation there. Well, this is more like a particle striking on the surface of the metal there. Now, that particle, that light, that radiation carries a certain amount of energy. And the energy of the light, however, has to exceed a minimum number. We call it threshold energy. In order for the release of the electron to happen, now any excess amount of energy beyond this minimum will go into the kinetic energy of the leaving electron, ejected electron. So the higher the the amount of energy carried by the radiation, the faster the electron moves when they are being ejected from the surface of the metal there. Okay. Now, based on the classical physics that we understand, if you have a moving object carries a certain amount of energy. Okay. When that moving object actually hits a particular surface, the energy is being transferred to other particles, say to the metal, to the particles inside, other particles inside the metal there. Now, with the energy exchange, some of those electrons may get excited, they get ejected. So according to the old theory, if you have a particular electromagnetic radiation, if it doesn't carry enough energy, well, energy can be accumulated. So you can just wait. There should be a delay. So after you wait for a while, and there may be enough energy collected, accumulated, and then the electrons will start to leave. Okay, so that was not what's observed there. Now, no electrons were observed until a light at a certain minimum energy is applied. So that defies the classical theory. Okay, so it assumed, well, based on the assumption there, if you have a moving particle that's not as energetic as we thought they are, well, energy can be accumulated. So the number of electrons, what experimentally observed is that the number of electrons ejected depends on the light intensity as long as that light is above the minimum energy. Now this minimum energy later on we call it ionization energy. The reason we call it ionization energy is that when metals, atoms of metals eject electrons, they become positively charged. As a result, they become ions. Okay? So you are ionizing metal atom there with the shine of radiation on the surface there. So this energy required is what we call the ionization energy, minimum energy there. So how do you explain the photoelectric effect? Well, Einstein published a paper on this particular effect there. So this is an example when you have the incoming light that does not carry as much energy, minimum energy required, you don't detect any electric current. As you increase the frequency, you're increasing the amount of energy there, and you start to see electric current being detected. If you double, after you go beyond that minimum energy there, if you double the frequency there, and you see a higher intensity of light, beyond the minimum energy required of the radiation there, and you see the increase in the amount of current being detected. So this indicates the electromagnetic radiation is moving like particles. Okay? There is a one-to-one correspondence. After you go beyond the minimum energy requirement, the threshold energy, as you double the frequency, as you increase the intensity there, okay, and there's more electrons being ejected there. So when we try to explain this based on the then current understanding, we can't explain this. The conclusion there is that based on this particular observation, there is a one-to-one correspondence between the ejected electrons and the light waves. Therefore, the electromagnetic radiation must be behaving like small particles. There's a certain amount of energy carried in each little particle, and we call it quantum, or photons. Now, photons, that's probably a term derived from earlier, the terms that we used, we started using earlier, electrons, protons, neutrons, and we have photons. So electromagnetic radiation or light, they actually behave like particles. We use the term photon. Now, what is the relationship between the amount of energy carried by radiation to the frequency or the wavelength, and the quantization of the energy starting here? So an object can gain or lose energy by absorbing or emitting radiant energy in quanta, a very small unit of energy. Now, this energy is being exchanged between matters or oscillators, or emitted as radiation. Okay, so in this case, the amount of energy carried by a particular radiation is proportional to the frequency. So E, the energy, equals to H times frequency. Now, since frequency equals to frequency times wavelength equals to the speed of light, we can keep on writing this equation, H times C over lambda. So that's the relationship between the amount of energy carried by the radiation to the frequency or to the wavelength. Okay, so this particular equation, H, is what we call the Planck's constant. Okay, so E equals to H times the frequency, or Hc over lambda, the wavelength there. That indicates light with longer wavelength or lower frequency will have lower energy. And then lights with shorter wavelength or high frequency have higher energy. Okay. We try to color code this. The red light happens to have longer wavelength than blue light. If you remember that visible spectrum, on the far left side of that visible spectrum, you see red color. On the far left side, you see the red color. On the far right side, you see the bluish and purplish color, and the violet color there. So a shorter wavelength means a higher frequency. Higher frequency means a higher energy. So this is something that we need you to remember, and this is the second equation. There are only 3 equations for the first learning objective that you need to remember. This is the second equation. Okay, so this is also known, this particular equation is also known as Planck's equation, also referred to as Planck-Einstein relation. Now, Max Planck and Albert Einstein, they work independently on this particular topic there when they studied the amount of frequency, the amount of energy carried by a particular radiation, and then as they published the paper there, and there's a lot of similarities. So eventually we come up with this equation. The energy carried by radiation equals to Planck's constant times the frequency, or Planck constant times the speed of light divided by the wavelength there. Pay attention to the units when you do the calculation.